he then moved to Olomouc to work in the group of radiophily. And now he's in Singapore at the A-Star Institute. Maybe you just say, because I understand it's not a university, it's more like
I'll explain that anyway.
Okay, and he'll talk about trajectory methods that he's been working in all the kind of his, say, stages of his career. So it's all yours.
Okay, thank you, Yeah, so my title is quite vague because I wasn't sure exactly what I would talk about when I was making it. And in the end, I decided, because I've had a little gap in my career, which I'll say about going to Singapore now, I haven't done any properly new work that we've finished off recently. So I'm just going to summarize the last couple of projects I've worked on. And a common theme of these is using trajectory-based methods to get interesting results in open quantum systems. So to start with, just to sort of summarize what Yannick was saying, I think I started off in the UK. I was working here in Warsaw for a while, quite a few years. I then went to Olomouc to work with Writing Phillips Group. And then I had an unexpected quantum jump in my life dynamics where I ended up in Singapore. So after a bit of time there, I started working at A-Star now, which is a research institute in Singapore. And just to give you a little background about what A-Star actually is, A-Star actually sits between like the universities and industry a little. So we do science, but we don't just do basic science for just doing like nice theory projects. So everything we do is tied in with real industrial applications. It's supposed to be projects that will attract companies to invest in Singapore, essentially. So it's a government agency with the idea that we attract external funding. So we work very closely with the universities as well, of course. So we work with, say, CQT over in Singapore, but also we work with industrial partners. So all the projects we work on have to have some kind of real-world implementation that is attractive to outside investors. And so specifically, I'm working in the Quantum Innovation Center in A-Star, and the work we do there is split into 4 pillars. So we have the quantum software and algorithms, we have the quantum photonic components, the quantum sensing and metrology, and the quantum materials and devices. So I'm actually split between the quantum software and algorithms group and the quantum sensing and metrology group. So in the quantum software and algorithms group, we do a lot of theory. It's completely theory in this group, where the large part of the package we work on is we have a very large-scale in-house software package that we work on. It's built on these tensor network emulators. And the idea is that this can simulate a wide range of quantum optical systems that will be useful for, say, quantum computing applications. So at the moment, there's around 40,000 lines of code in this package, I think, and it's constantly growing all the time to incorporate more and more different platforms. Within the quantum sensing and metrology group, we do a variety of tasks. One such task is in levitated systems. So here there are some platforms where they can make little objects levitate, and they do this through optical methods, through magnetic methods. And these obviously have a wide range of applications. These levitated devices are very interesting for gravimetry, for instance. So this is real technology that people are trying to accomplish, and we're doing the science to help support this. So we work closely with people at NUS, NTU, the University in Singapore, but we have a number of industrial partners as well. And we also have lots of opportunities. So A-Star is a very big center. It employs thousands of scientists. And even in the Q-Inc ourselves, we have well over 100, I think. And because of this, there are a lot of funding opportunities, particularly for PhD students to come and spend some time working at A-Star through their ARAP program, and also the postdoctoral program, which is called AIP. So if anyone is interested in finding out more, please feel free to email me, or if I'm trying to be more involved on the social thing, you can scan this and connect with me on LinkedIn. So that's what we should be doing now. If anyone wants to discuss more, I can tell you more about what goes on at A-Star. Okay, but now on to science. So what I thought I'd do today is I would just give an overview of the sort of common elements of what generally most of my research has been about, which is open systems, stochastic dynamics. And I'll talk a little bit about how you simulate these systems, and what methods we can use to help make these simulations better, faster, more accurate. And then I'll just summarize some of the work that I've been doing, some applications of this theory. The first is a quantum sensing paper that we put out recently with Yannick. And another is a project I was working on in Olymus with the group of Redding Philip, where we're trying to do some non-Gaussian state generation through continuously monitored systems. This one is a work in progress, so the results are a little sketchy at the moment, but I'll sketch through what we've done so far. Okay. So just to start with, the basic terminology, just so it's all consistent what I'm talking about. So when we have an open quantum system, what we mean is we have some internal state, which is generally our system of interest. This has some internal Hamiltonian, Hs, and it can be driven, which we describe by Hamiltonian Hint. And then we have a Hilbert space for the BAF as well. And we characterize this through some, again, Hamiltonian that describes the BAF's free energy. And typically the BAF we will model as some infinite dimensional system that thermalizes rapidly, has infinite degrees of freedom, whereas the system we're interested in is more contained. So it could be, say, a two-level atom, and the BAF it interacts with is just the electromagnetic field that surrounds it. Then the standard way we model such a system is we derive the master equation, which I'm sure most of you should have seen before. And it's just the sum of the closed system dynamics, essentially, due to the local terms. And then a Hamiltonian describing the system BAF interaction manifests in the form of a dissipator here, which has this form here, which is in what's known as limb-like form here. And we assume that we take the usual Born-Markov approximations, rotating wave approximations, etc., just for simplicity here. Now, the first thing I always do when I take the Hamiltonian is, the master equation, is I rewrite it in a form like this, where I absorb the part of the dissipator into the Hamiltonian in order to make this a non-Hermitian Hamiltonian, which I call a conditional Hamiltonian. So, yeah, I always rewrite the Hamiltonian to be this conditional Hamiltonian here. And that allows you to write the master equation like this. And at this point, we haven't changed anything, we've just written it in a different way. But because I'm always interested in jump-type processes, this is a very physically motivated way to write the master equation, because we separate all the terms here that correspond to no interaction into the BAF in one term here, and the terms that correspond to some interaction or decay or absorption from the BAF into these terms here, which we call the jump terms. So this gives us an obvious way to write down some sort of Krauss decomposition of the dynamics, where we split the dynamics into, as I just said, the parts where we have no interaction, so no emission, no absorption. And because we have something like a Hamiltonian here, okay, it's a non-Hermitian Hamiltonian, that means the time evolution of the system can just be written as the unitary evolution, which is the exponential of the conditional Hamiltonian. So this is our K0 Krauss operator. So this operator applied to our state corresponds to the evolution of the system when we don't measure anything in the back.
But it's not unitary.
It's not unitary, no. So we write it with the standard unitary, okay, the time evolution unitary, but of course, exactly. The Hamiltonian itself is conditional, non-Hermitian. So this gives a decay in the size of the state that we have. And actually this is important later, because then the absolute size of your state vector or density matrix corresponds to the probability of this emission occurring. And then for the jump terms, we can define our Krauss operators for when jumps occur. For a jump of type I is Ki, And you can approximately define this as just the square root of decay rate times the infinitesimal time times your Lindblad operator. So naively, you now have a way to simulate your system across some specific trajectory. You can impose some kind of dynamics on your system, calculate the probabilities of what occur. But a nice way to write this first is in the form of a stochastic master equation. And just to physically motivate where this comes from, this is why we introduced the Krauss operators before. We still have the continuous evolution along not detecting anything, because the obvious reason is because this is the dominant process. Most of the time we won't see anything if you choose a small delta t. If you have an infinitesimal delta t, your system will continuously evolve along this pathway. But then we introduce the jump term here, and the jump term corresponds to a term that just renormalizes the dynamics for when you don't have a jump. And then you impose the jump, and you reset your system. So this is why you end up with dividing by the tracer, subtracting the original state of your system. And here, this dn term is called the Poisson increment, and the weight of this Poisson increment describes how likely a jump is to occur. So this goes back to corresponding to, like when I was saying with the Krauss operators to the jump, these have small size. When you apply a Krauss operator to a state, then the size of the state afterwards is the probability of that jump happening or this evolution happening. The same is true for this Poisson increment. So this is a random element, and you build this into your simulations, which I'll talk about next, in order to actually generate the dynamics or the probability of certain dynamics occurring. Now, what we've considered so far is what's known as a full unraveling. So when you have a full unraveling, this means that all the decay processes you unravel in such a way that you have the jump-like term for them. So for all the processes here, we sum over all the decays and we write down the specific jumps. Jump operators for them here with their respective weights. But this isn't necessarily a physical thing to occur, because if you have some kind of system where maybe you have optics and mechanics, an optomechanical system, which I'll talk about later, then okay, you can monitor the light coming out of the system. You can put a photon detector there, you can do some homodyne measurement on it. But first of all, your detector might not be perfect, so you might not see all of the light coming out. And so you have some unobserved channel for the light. You also have the phonon interactions going on with the bath. And we can't monitor the phonon interactions, we can't build, in these systems, a phonon detector. So if we have some unobserved jumps, we need to account for these somehow. We can't we can't say a jump has happened if we haven't seen it. And so for these terms, we need to restore the original Lindbladian dynamics, where we take the ensemble for these. So our stochastic master equation becomes split into our smooth, not observing anything evolution, averaging over the unobserved jumps, and monitoring for the jumps we are actually observing for with some stochastic terms. Now, there's a difference in the way we can monitor these systems, model these systems, depending on the type of interaction we have, which is actually very crucial to the computation of such system. If we have a full unraveling of the system, then if we look at the dynamics of this kind of equation here, we see that actually at all times our system will remain in a pure state. We never have anything that brings it to a mixed state. If we apply this conditional evolution to our system, our state will remain pure. We start in a pure state. If we apply a jump, we are resetting it exactly, so it remains in a pure state. It's only when we have some kind of averaging of the ensemble that we lose our pure state, have a mixed state, and therefore need to deal with the density matrix. So this means, if you're modeling your system, if you have some kind of unobserved loss, you need to use a density matrix and the stochastic master equation, and your object size that you need to control and monitor scales around n squared. But if you have a full unraveling, where you can just monitor the state vector, then you only have an object of size n that you need to track. And this means as you get to a very large system size, the computational power that you need to model that system is much smaller if you can consider the full unraveling. So this is definitely a computational advantage. Okay, now if we were to actually model these systems, the theory of how you would do this goes back to the 90s mainly. These are the main collection of papers that I generally always cite for these quantum jump approach models. The methods that we use to simulate the systems have definitely advanced since these papers were first introduced, but the idea remains the same. So basically, if we have an evolution along not observing a photon, say, then all you need to do is apply your time evolution operator to your state, then draw a random number essentially. If your random number is less than the probability of a jump occurring, you have a jump. If not, you don't have a jump and you keep repeating your no jump dynamics. This is the simple methodology of how these simulations were first proposed to be done. And upon doing this, you eventually end up with some kind of click pattern, which I always call a barcode, and you have some data. So either you could use this method to generate your data yourself in the first place, or calculate the probability that occurs by calculating the probability of each specific step in your dynamics. But we've come a long way since the 90s. There are ways that we can improve these simulations now, make them much more efficient, so that we can solve much bigger system sizes. We have better computers, we have better methodologies, so now we can do a lot more. Okay, so firstly, the main improvement is instead of piecewise evolving the system by delta t each time, instead we can solve a large set of simultaneous ODEs. So if we have a density matrix, we can put this into the stochastic mastery equation, and we have an expression for each element of the density matrix. It's some kind of differential equation, and we can get the machine to simultaneously solve these equations, and we can evolve it up to some time that we want. So instead of testing for a jump at each time step, we sample from the distribution, and we say, okay, we'll have a jump when the probability of no photon gets down to some specific value. So now we can solve this set of differential equations up to a point, and then enforce the jump. So this means we don't have to do everything step by step. It reduces the chance of having some kind of machine error from applying your delta t each time. Generally this will be faster. And we have some control over this as well. We can set the absolute tolerance and the relative tolerance of the solver. Okay, it will affect the speed, but we can control this somehow so that we can control how precise our solution is. So in principle then, we can solve for up to a long time, one step, rather than trying to piecewise keep iterating our system. The techniques you can do to also further manage errors, such as making sure the diagonal of your density matrix is behaving properly. Generally the errors really come in from if you don't have coherence matching, but you can fix this by actually, if you're smart in the way that you define your differential equations, then you don't need to solve for opposite ends of the coherences. You know they should be the complex conjugate of each other, so you only solve for one of them. You set the other one to be the complex conjugate, so this saves you computational time as well. And generally this is where the errors usually come in simulating these systems. You get slight mismatches in the coherences just through the machine precision. And then as you evolve your system, you can start to end up with complex elements along the diagonal, which we shouldn't have. These tiny, tiny errors can actually lead to drastic effects in the evolution of the system. So it's something that you have to be really careful of when you're solving the dynamics. The other optimization you have to be careful of is determining the size of the Hilbert spaces you need. And this is really important for quantum trajectory approaches, because you can have a system where you could maybe solve the ensemble dynamics, you could solve the master equation, and you see that on average the energy in your system is very low. So naively you might think you just need a quite small Hilbert space, you don't need very high Fock states that you're simulating. But actually along the conditional dynamics, these can fluctuate quite a lot more. Especially when you have a jump, you can then force your system into higher Fock states. So this is something that needs testing for quite carefully to make sure your system is built in such a way that it can handle high excitations that you might not necessarily think you need from the ensemble evolution. But after you do all this, you try to optimize as much as you can the size of your space. Then, in principle, you can do the full quantum jump trajectory simulations through these methods. You don't need to do any reduction of classes of the states, like matrix product states, unless you have a super large system. This is pretty well simulatable still. Now, one of the good uses of generating quantum trajectories is actually for Monte Carlo methods. So in Monte Carlo methods, this is used quite a lot in very complex systems where maybe we can't solve the dynamics of the system in the first place, so we don't even know the ensemble evolution of the system. Or maybe we have a way of generating a sample of our system very easily, but we don't have a good way of solving the full dynamics of the system. And in this case, because of these advantages of being able to generate trajectories, if they're pure states, very easily, compared to a large density matrix of size n squared, then we can do this quite efficiently. So because the memory requirements of our system are much smaller for n, the speed at which we can generate trajectories and average over them can be much quicker than trying to solve the dynamics of a system that is n squared. And of course, if you generate enough trajectories and average over them, you should reproduce the ensemble dynamics. This is by definition how they should behave. One catch of this that you have to be careful for is that this only makes sense as long as your system is ergodic. So the ergodic principle is that the time average matches an ensemble average. So if you have a non-ergodic system, then of course averaging over many trajectories won't reproduce the ensemble dynamics because the principle of the time average, which is essentially how you calculate the ensemble average, isn't going to match the how you ensemble over your trajectories. But generally in quantum optical systems, this is all true. This is mainly an effect that comes into play in some condensed matter systems where non-ergodicity is a factor. Okay, nearly finished on this bit now, but the final thing I want to say about trajectories in general is quantum trajectories are very cool in general to look at compared to the ensemble. Because even if you have a Markovian quantum system, it has a Markovian evolution, the trajectories along your quantum system, the data that you produce from them themselves are non-Markovian. And you can see this by just considering these Krauss operators here. If we consider some general Krauss evolution of probability of observing some x3 after we've observed specific x2 and x1, this is not the same as observing x3 just after x2. So the data that you generate from a trajectory, or say the photon click pattern, itself is correlated, even if your system itself could be uncorrelated. The internal dynamics could be uncorrelated in some sense, but the emission statistics can be correlated. And this means like a trajectory itself is a very useful quantum resource, and it can have powerful applications in sensing, as we'll see. Okay.
So unless Krauss operators are rank 1, yes? If they're rank 1, then I think it's true. No?
Yes, I mean, okay. There are definitely cases where what I put there is not true, but in general, these two don't match. If you have the Markovian, if you put a general Markovian map for the first time, then these two won't match. But of course, there are cases when they will match. Okay, so now I've kind of summarized the sort of theoretical background, maybe quite fast, of the common themes between the work I've been doing in the past. So now I'm just going to summarize some results from two projects I've worked on over the last couple of years. So the first one is the sensing project that I mentioned. One other common theme between these is that they are optomechanical systems. We're fairly short on time, so I won't go into too much detail on how they behave exactly, but just to give a picture of these systems. This is essentially, I always picture them as a mirror on a spring. It's the easiest way to imagine it, but it's the same theory for, say, like levitated systems, for instance. It's just light interacting with some mechanical element. And the Hamiltonian describing such a system is you have some like detuning of the optical mode. The mechanical mode, you have some nonlinear interaction between them and some driving. Fairly often people linearize this interaction, which is well justified if you have very strong driving or your interaction between the optics and mechanics is quite weak. And in such a case you get a linearized Hamiltonian like this. So now the dynamics are much simpler. This Hamiltonian describes the evolution of the quantum part of your system. So it describes some quantum fluctuations essentially for mostly classical coherent state-like internal dynamics. Yeah. Then using these methods you can write down your master equation of your system, just like we had before. Now I've subbed in some actual specific decay rates. We can write down a stochastic master equation, so this is how we would simulate such a system. For the partial unraveling, based on what we can actually see, we have like equation 12 here. But if we have the full unraveling of the system, then we have these 4 jump-like operators. So the thing to emphasize is the top one here corresponds to what you would actually see. Okay, we can only detect photons, so this is the physical process of our system. But for mathematical purposes, we could simulate trajectories that generate all the jumps that happen, and then later average over them in order to reproduce the ensemble dynamics. Okay. So basically what we want to do is we want to be able to infer some information about a parameter based on a single trajectory. And this means, okay, we can then continuously monitor the system, so we use this stochastic evolution. And based on this stochastic evolution, we estimate the value of some unknown parameter. So pictorially, this is generally how these kind of sensors work. You have something that drives some system that depends on some parameter. You detect it, you have some signal, and then from that you infer the value of the parameter. Often people will talk about frequentist methods with Fisher information. That's not relevant for us here because we want to consider a Bayesian evolution. This is the more natural way to imagine inferring information from such a system. And the idea is here we build up a posterior, which is our belief of the value of the unknown parameter. And from this posterior distribution, we can make an estimate which will be the mean of the posterior. It's the optimum way to estimate the value of your parameter. And in order to get this, we can generate the likelihood of our certain data being generated as a function of the unknown parameter by using these stochastic methods that I was describing before through the stochastic master equation. And if you do this, just to summarize basically how this works, you would propagate your dynamics through. So let's say you have some photon click pattern. You propagate that click pattern through your stochastic master equation for a range of different values of the unknown parameter. And from this, you have the likelihood for each. You can build up your posterior distribution. And you can get nice results like this, where as you start not knowing anything potentially, but as time goes on, you learn better and better where your what the value of the parameter actually is. For the nonlinear optomechanical system that we consider, there are some specific values that are particularly good for this, which we call n equals 2, n equals 1. For the purpose of now, don't worry about what they are, they're just good parts to sense. And we found that this works very well. This methodology is great. You get very good accurate sensing just from a single trajectory. But the problem is this is computationally very, very intensive to do because solving the dynamics of these systems takes a long time. Okay, it's a complex system. We're generating a lot of data, propagating it through a long time. And that means you can't do it online. Essentially, this would take around 1 to 2 days, even on an HPC, to generate one of these figures here. So it's not practical. So instead, we want to use some kind of sampling methods in order to improve the efficiency of this process. And if you look in the literature, you find many, many sampling methods. People quite often talk about particle filters, Markov chain Monte Carlo methods, the Metropolis-Hastings algorithm. But the problem for us is this emphasizes on simplifying this integral. It avoids doing this integral. And what we need is a way to simply determine the likelihood, this expression here. And this is where we come in to an algorithm that's known as ABC, approximate Bayesian computation. And the idea of this is it gives us an efficient way to generate a posterior without ever having to actually calculate the likelihood. And it works like following. I'll just quickly summarize how the algorithm works. Firstly, you prepare some library of trajectories. And the useful thing here is we can use the method of just generating a state vector with all the jumps that happen. We'll only use the jumps that correspond to photon clicks that are detectable, but our library can be created from the ones where all the jumps occur, because in the end we're going to be averaging over this library somewhat by the sampling. Then you get the averaging effect that restores the physical ensemble behavior of the system. So this means we can generate the library more efficiently, and then the evolution of the system, etc., is done easier. We then draw many, many samples from this library and compare it with our target trajectory that we want to do the sensing on. And we apply some kind of statistical test to determine whether this sample is close enough to our true target trajectory. And we repeat this over and over again until we have built up some distribution of our samples. And it can be proven that if you do this long enough with good enough statistics, then this distribution that you build from the sample will reproduce the posterior distribution. So just to skip over, this is just what I explained with the algorithm. But in the end, what you get is very nice results where you can reproduce the posteriors very well. So you can see, you can notice it, but the black line corresponds to a brute force posterior that takes me like a day or two to actually generate. And these colored lines are some sampling methods through ABC where I try to reproduce the posterior. And to reasonably good accuracy, they can generate the posterior very well. And there is a huge speed up on this. So instead of the process taking 1 to 2 days on an HPC, once I have my library, I can run the algorithm, and within around 5 minutes just on my laptop, I can produce these posteriors. So the speed up is enormous. There is a lot of accuracy. And this is particularly true when we consider the nonlinear system where the dynamics are much more complex. So here we see, okay, it kind of works for some values that we're trying to sense, but for other values it's not very good. It's pretty bad. And the reason for this was because we chose bad summary statistics. We can improve it slightly at the cost of quite a lot of noise in the posteriors that we generate. But now, at least, we see they're more focused around the right areas. So it's a game of trying to choose the best statistics to do the job. But the speed up is enormous, at least. So then, at least you can have some estimate of the posterior in a reasonable amount of time. So that's the summary of the ABC part, the sensing part that I'll talk about. And to finish off, I'll just talk briefly about the work I started in Armets, which is still ongoing. This project was again using optomechanical systems and quantum trajectories. But in this project, what we wanted to do was use these trajectories to generate interesting quantum states. So instead of having to post-select or something like this that's very inefficient in order to generate some interesting non-Gaussian state, we want to know, can we just monitor a quantum trajectory, and then based on the signal that we see along the way, maybe you can form some feedback on this, maybe you can like change the detuning online as you go, something like this, change some of the driving properties of the system. But can you generate continuously as you go towards interesting quantum states? Now in this project we considered the linear version of the optomechanical system, And I'm going to take one further step here and just emphasize some physical properties that the detuning has on the system. And here we have, if you choose red detuning, then you can do a rotating wave approximation on this Hamiltonian, and you end up with a beam splitter-like interaction here between the optics and the mechanics. If you have a blue detune system, then you end up with a squeezing-like interaction between the optics and the mechanics. And what this physically corresponds to is if you have a red detune system, then the only way I can generate a photon in my optomechanical system is if it absorbs a phonon. So this term here creates a photon in your optomechanical system by destroying a phonon. Then, if you detect a photon coming out of your cavity, you know you must have destroyed a phonon in the cavity as well. And this is the principle of how like photon counting based cooling works, for instance. So if I have a red detune system, if I detect a photon, I'm projecting my system into a cooled state. But another cool thing about this is actually if you have the right kind of parameters for your system, in particular this top left one here, where you have a very fast cavity decay rate compared to the optomechanical coupling and the mechanical decay rate, then you can actually infer the phonon correlations of your system through the photon correlations. So if I monitor the G2 function of my system for the photons coming out of it, this will correspond exactly to the phononic G2 function. So one of the things we did first in this project, just to understand this better, is we considered different values of the parameters to see when this breaks down. And we see this is heavily reliant on having a much faster cavity decay rate compared to the other internal processes. And this is because then if a photon is created, it is almost immediately lost. So none of the other internal processes of the system have a chance to create any effects in the system. It's not, phonons aren't lost through thermal decay, they're really lost because a photon is being created and then emitted. Okay, so this is just an insight into the physics of the system, but what we actually want to do, like I said, is generate these interesting quantum states in our system. And this is important because people need good ways to generate CAT states, GKP states. Generating GKP states is an exceptionally hard problem to do. But if you could maybe online create one rather than having to post-select through very low probabilities, this would be a big advantage. So, okay, maybe this is a bit too ambitious, but still, what interesting states can we create? And actually, you can create some kind of interesting states just along quantum trajectories in these systems. So here on the top row, I'm plotting the Wigner function of the mechanical part of the system and the optical part of the system. In the optics, not much interesting happens, but in the mechanical part, you get negativity of the Wigner function, which is a sign that you have some non-Gaussianity in your system. So you're definitely creating some interesting mechanical states as you go. We can see from the Hinton diagrams on the bottom, so this is my, essentially the population of the density matrix of the system. It's well contained within my Hilbert space, so this is good. It matches the criteria I said that we need to make sure we're not bleeding out at the edges. It tells us a little bit about how the density matrix looks. So we can see, okay, we don't have anything too like a cat state, but closer to a cat state than if we still had a Gaussian state. So it's making some kind of interesting states. Sometimes not much happens depending on the parameters you choose, the red detuning, etc. So it's all about trial and error, trying to understand what parameters are interesting to choose for the system. This is ongoing work still. But when you have these kind of states, like I was saying, one interesting thing is, okay, it's not a cat state, but I could project onto a cat state. And the probability of projecting onto a cat state will be larger for these systems that have some kind of fringe behavior already than those that don't. So it might be a way to more efficiently create these kind of more exotic quantum states. Again, this is still early work, So there's more to be done still on determining actually how efficient this process would be. So I think I've gone a little bit over time, so I'll just leave the summary up here. So hopefully you understand a bit about continuous measurement theory that is applicable. You agree that it's useful to these systems. And if you want to read more about these projects, then we have some papers here for the sensing one. So the latest one just came out around a month or so ago. And hopefully this one with the group enormous will be done soon. Thank you.
Thank you, Luis. So let me ask the questions from the floor. If there are any, yes, there's one.
I have a question regarding this ABC algorithm.
Sure.
So are those trajectories drawn from the uniform distribution, or there's any pre-selection of the distribution
okay.
of
So I just repeated, so it's recorded. So the question is an ABC algorithm, you get trajectories, are they from the uniform distribution? So maybe the answer is how to generate these trajectories in the library, right?
Yeah, so the distribution that we draw them from is actually from your prior knowledge of the system. So your Bayesian case, you have a prior, which is your understanding of the parameter, and then you weight the value that you draw from, you sample from, based on the prior. So this is how you get the prior into your dynamics. The results we have here, we consider a flat prior, so it is the uniform for us. But
yeah, I think maybe so you want, because so you want the distribution of the trajectory or the parameter that you're trying to estimate, because he's answering the parameter first.
Yeah, because I believe that the idea of this algorithm was based that we have a lot of the trajectories that we are inferring information from, so I was wondering whether we can somehow minimize the number of required trajectories to generate, just to generate the ones that will really help us. Information in advance.
So yeah, you're right. There definitely is a certain point where we don't need any more trajectories. Like you can see, the insets of the plot here is how quickly it converges to the true value, and generally this is pretty quick. But for the library, the idea is you want to be able to build your library so that you can save it. So you don't want it tailored to the one trajectory that you're trying to sense, otherwise you'd have to generate a library each time. You want your library to be as full as possible, so that then if someone comes along with a new trajectory, you can just run it, 5 minutes later you have your posterior again.
Okay, so maybe I don't know if you would, but I would just make a library for a very dense grid, and then on Monday you come to me with some prior distribution. You know that your parameter is around 10 plus minus 1, right? But then you will actually sample from that 10 plus minus 1. So you just use the ones from the library that are around there. No? Okay. And the library is done in advance, so you can, I don't know, use a supercomputer and do it, you know. It's there, it's just getting from the memory. No?
So following up on this question, so the longer you measure, the more precise your estimation will be. So somehow when you generate this library, you have to know for how long you measure, because you need to set this grid,
Yeah,
yes,
exactly. Yeah,
for making it work. So I was wondering if there is some way that you can say, okay, that interesting things happen on some time scale, and then we approach some, I don't know, stationary regime where you can just extrapolate simpler what happens next. I mean, did you consider this?
Yeah, it's something we thought about, considering just, say, the early part of the dynamics is maybe different to the later part. Stationarity as well, so maybe you could combine the trajectories somewhat, like if I add two trajectories together, if they're approximately in the stationary regime, then the click patterns have become quite uniform at some point, so this would be a way of extending it. It should work fairly well in these cases, like the system we consider here anyway, it's stationary pretty fast, so if you look at the click patterns, they do become pretty uniform quite quickly. But yeah, that is a drawback anyway. It's, you know, your library has to be designed to your experiment in some sense for it to be exactly like that. So if you change the experiment, you would also need a new library.
Unless you have a big one with not dense grid and yeah, but I think Rafa's question is, it's not a secret that we are cheating here a bit, because this is all motivated by real-time sensing experiments, and then we fix the number of clicks, right? To be able to plot something, right? I think the long-term story that we are already working on is you really need now to adjust this ABC to work in real time. So you get clicks and it updates. So the natural way is actually to do machine learning, and we're still doing it now with fixed clicks. But I think the way forward, which was done and we'd like to learn it, is reinforcement learning. So you have some agent that, based on the model you gave it, it's now, as the clicks come in, it's updating it better and it's learning on the way. So this sort of unsupervised machine learning algorithms, right? And now they are cheaper than strawberries.
Yeah, I feel like the way you could do this with ABC, in the sense that you could, you prepare your library for a number of parameters. You could also prepare it for a number of different control factors that the reinforcement learning would do effectively, and then depending on how it's going, you would switch to a different library to do the sensing. But then probably, the machine learning is probably going to become more efficient anyway at some point. So.
Okay. So any more questions? So I have a short question, because for the second project you said something like, I projected onto a cut state.
Yeah.
What does it mean physically? You actually you just, it's an overlap with the cut state? Because my question is, can they actually project onto cut state in real life?
Yeah, I mean, if you had some kind of, you built your system and then you had some detector setup that detects it, it'd be like some kind of post selection. So then if your detectors click in a certain way that corresponds to some kind of cat state, then we remain in a particular state.
But it's a bit of science fiction, because they probably have only photon addition, photon subtraction, and this is not really. Okay, so it's just to check.
It's theory for theory's sake at that point, yeah. I mean,
Okay,
realistically, it'll be more based.
For maybe they can do something, but not yet.
Not that I know of exactly, no. But it's kind of motivated by the same way, in the sense of when you're trying to create a cat state or by
To be closer.
GKP states, you project on these like super high photon number states. Just applying the same algorithm just to see what happens.
So with that, let us thank Louis again.